Mount Etna is collapsing into the sea, triggering a mega tsunami. What's happening right now on Europe's most dangerous volcano could unleash a Mediterranean catastrophe that makes the 2004 Indian Ocean disaster look like a gentle wave. Picture billions of tons of volcanic rock sliding into the Mediterranean Sea in a matter of minutes, displacing massive amounts of water and creating tsunami waves that could reach heights of 100 feet or more. This is not science fiction. This is the terrifying reality that scientists are tracking as Etna's southeastern flank shows all the warning signs of catastrophic collapse. But here is what has volcanologists in complete panic. The collapse is not a distant threat. GPS monitoring shows the volcano's flank is sliding toward the sea at accelerating rates, while the massive 100-foot fracture that recently opened follows the exact same pattern as the prehistoric collapse that happened 7,200 years ago and reshaped the entire Mediterranean coastline. The most chilling discovery came from analyzing ancient tsunami deposits across the Mediterranean. The last time Etna's flank collapsed, it generated waves that traveled over 1,000 miles, devastating coastlines from Sicily to North Africa and wiping out entire civilizations that had no warning of what was coming. Is Mount Etna's collapse the countdown to a mega tsunami that could kill millions across the Mediterranean? Or do we have enough time to prepare for a disaster that could happen within hours of the first major landslide? Mount Etna towers, 3,357 meters above Sicily's eastern coast, a height that shifts constantly as eruptions build the summit higher, while gravitational collapse tears sections away. Europe's tallest and most active volcano was not born on stable geological foundations. It emerged from one of the most violent tectonic collisions on Earth, and that same violence is now destroying it from within. The African tectonic plate dives beneath the Eurasian plate directly under Sicily, a continental collision that began millions of years ago and continues with relentless force today. As the descending African plate melted deep within the Earth's mantle, superheated magma forced its way upward through fractures in the crust, building layer upon layer of lava and volcanic ash until Mount Etna emerged as one of the planet's most powerful volcanic systems. But the forces that created this geological giant are the same forces, tearing it apart. Unlike stable volcanoes rooted in solid bedrock, Mount Etna's foundations rest on fractured, unstable ground. Ancient marine sediments from when this region lay beneath the sea now form part of the volcano's base, shifting and compressing under the immense weight above. The volcano's steep eastern flank sits directly atop the Alto Etna fault system, a network of massive offshore fractures running beneath the Ionian Sea. This fault network acts like a conveyor belt, slowly dragging sections of the mountain toward the ocean depths below. Etna's growth pattern has been catastrophically uneven. Its eastern slopes have swollen over centuries as lava flows pile higher and magma intrusions inflate the mountain's interior. These magma chambers expand and contract with each eruptive cycle, creating internal pressures that fracture the rock from within. The combined assault of gravity, tectonic movement, and internal magma pressure has pushed Mount Etna into an unstoppable drift toward the sea. The volcano keeps building itself higher through eruptions, even as its massive eastern flank is steadily pulled seaward. Scientists describe Mount Etna as a volcano caught between two opposing forces. It is being constructed through ongoing eruptions, even as gravitational collapse tears the entire structure apart. The mountain grows upward while simultaneously sliding toward its own destruction. Mount Etna's eruptive history stretches back over 2,500 years of recorded human observation, with ancient Greek poets and philosophers writing about the volcano's terrifying power and fiery temperament. Since 1500 BCE, more than 200 eruptions have been documented, securing Etna's reputation as one of the world's relentlessly active volcanoes. But beneath this dramatic history of fire and lava lies a quieter, far more ominous story that scientists are only now beginning to fully understand. Geological evidence reveals that Mount Etna has suffered several massive flank failures throughout its violent history. The most striking remnant is the Valle del Bove, a vast horseshoe-shaped depression carved into the volcano's eastern flank. This enormous scar measures 5 kilometers wide and plunges 1 kilometer deep, the unmistakable signature of a catastrophic landslide that occurred tens of thousands of years ago when a massive section of the mountain simply gave way. But the evidence of Etna's destructive past does not stop at the coastline. Offshore scientific surveys have discovered huge fields of volcanic debris scattered across the Mediterranean seafloor, the remnants of submarine collapses that occurred approximately 8,000 years ago. During these events, enormous sections of Mount Etna plunged directly into the Ionian Sea, displacing massive volumes of water and triggering tsunamis that devastated coastlines across the Mediterranean. Sediment analysis confirms these collapses were catastrophic and sudden, occurring within minutes rather than over gradual geological timeframes. The pattern continues into the modern era with terrifying consistency. The deadly 1669 eruption buried entire villages and sent molten rock flowing to Catania. Later eruptions in 1928, 1971, 2001 to 2002, and 2021 repeated the same worrying pattern. Fissures opened along the southeastern flank, and instruments recorded the mountain inching steadily seaward with each volcanic event. Each eruption subtly deforms the mountain's structure, creating new fractures and exploiting existing weaknesses. Scientists now understand that Etna's entire structure is behaving like one vast, slow-moving landslide, driven by magma pressure, gravity, and tectonic strain working together. The 8,000-year-old collapse triggered a Mediterranean tsunami when Sicily's population was minimal. Today, over 1 million people live directly in the path. For decades, geologists believed that Mount Etna's flank motion was driven primarily by magma pressure building within the volcano's internal chambers. That fundamental understanding changed completely between 2016 and 2018, when researchers from the Geomar-Helmholtz Center for Ocean Research and INGV deployed a network of underwater acoustic transponders along Etna's submerged southern flank to measure seafloor motion with unprecedented precision. What they discovered shattered every assumption about how Mount Etna was collapsing. In May 2017, the underwater instruments recorded a 4-centimeter shift occurring over just 8 days, a movement that happened completely without any volcanic eruption or earthquake to trigger it. This slow slip event revealed something never documented at any volcano on Earth. Mount Etna's entire southeastern flank, including massive sections beneath the Mediterranean, was sliding as one enormous block measuring several cubic kilometers in volume. The flank was no longer being pushed by magma. It was being pulled by gravity itself, the mountain's colossal weight dragging it toward the ocean floor below. Monitoring showed this gravitational motion often accelerates after major eruptions or earthquakes, demonstrating how fragile the system has become. Satellite data and ground-based GPS stations confirmed the sliding continues relentlessly today. Between 2021 and 2024, following several powerful eruptions, scientists recorded renewed deformation across the volcano's summit and flanks. High-precision instruments detected movements measuring millimeters per day, accumulating into meters of displacement over years. Swarms of small earthquakes have rattled the region with disturbing frequency. The most alarming discovery is that offshore tectonic shifts and surface movements are now occurring in perfect synchronization, suggesting the entire system, from seafloor to summit, is moving as one interconnected failure mechanism. In 2024, radar studies indicated accelerations along the submerged Alto Etna fault system, the same zone that hosted submarine landslides 8,000 years ago. Researchers warn that although collapse is not imminent, Etna's flank is sliding faster and across a larger area than ever observed before. The process has already begun. Scientists can measure it and track it, but they cannot stop it. June 2025 marked a dramatic escalation in Mount Etna's volcanic unrest, as renewed explosive eruptions sent towering lava fountains hundreds of meters into the sky above the summit craters. Ash columns rose high above Sicily's eastern coast, visible for dozens of kilometers, and forcing temporary airport closures as volcanic debris drifted through commercial flight paths. The intensity shocked even veteran volcanologists who have spent decades monitoring Etna's behavior, because this was not just surface activity releasing pressure from shallow magma chambers. This was evidence of deep magma intrusion, forcing its way into the volcano's weakest zones. Persistent seismic swarms rattled the region throughout July and August 2025. Monitoring networks recorded hundreds of small earthquakes concentrated along the southeastern flank within just weeks. The earthquake pattern was not random, but showed clear linear progression, suggesting magma was forcing open new pathways through fractured rock already at its breaking point. Each tremor indicated another fracture opening, another weakness exploited, another step closer to catastrophic structural failure. The timing coincided perfectly with dramatically increased ground deformation measurements recorded by GPS stations positioned across Etna's unstable southeastern slopes. High-precision instruments detected surface movements exceeding anything recorded during previous eruptive cycles, with some monitoring points showing displacement rates that doubled or tripled compared to baseline measurements. The deformation was concentrated precisely in zones geological surveys identified as most vulnerable to collapse. What the combined data reveals is deeply alarming. Magma is not just erupting from Etna's summit anymore. Magma is intruding laterally into the already weakened southeastern flank, forcing its way between layers of fractured volcanic rock and ancient unstable sediments. Each injection of superheated magma acts like a massive hydraulic jack, adding both heat and pressure to slopes already sliding under their own weight. The magma intrusions are pushing the mountain apart from within, while gravity pulls it downward toward the sea. Scientists describe this as a dangerous feedback loop that accelerates with each eruptive cycle. Eruptions inject fresh magma into the flank, making the slope heavier and more unstable. This instability triggers earthquakes as rock fractures under stress. The earthquakes allow the slope to slide more freely, creating space for additional magma to intrude. The cycle repeats and intensifies, each iteration bringing the mountain closer to catastrophic failure. Comparison to historical patterns makes the current situation even more terrifying. The activity in 2025 mirrors conditions that preceded major flank movements in 2002, when significant eruptions caused measurable displacement. But current deformation rates do not just match those events. They exceed them by margins, forcing scientists to recalibrate monitoring thresholds. Deformation rates are now pushing instruments and protocols to their limits. The mountain is moving faster now than at any point in recorded history. Each eruption, each earthquake, each centimeter of measured displacement brings the moment of catastrophic collapse closer to reality. If Mount Etna's unstable southeastern flank were to suddenly give way, the catastrophe would unfold with a speed that makes evacuation virtually impossible. In the worst-case scenario, scientists have modeled extensively, billions of tons of volcanic rock would collapse into the Ionian Sea within minutes. The trigger could be a massive earthquake, a major explosive eruption, or the slow gravitational sliding simply reaching a critical threshold where rock can no longer support its own weight. The moment of failure would be instantaneous and irreversible. Upper slopes would fail first in a catastrophic landslide, with rock debris accelerating down the mountainside and hitting the Mediterranean at tremendous velocity. The impact would displace massive volumes of water instantaneously. A tsunami wave would form within seconds, rising 20 to 30 meters high, as the ocean responds to billions of tons of rock, suddenly occupying space where water existed moments before. The wave would race toward Sicily's eastern coast at hundreds of kilometers per hour, moving faster than any evacuation. The city of Catania, home to more than 300,000 residents, sits directly in the tsunami's path with almost no time to react. Within 5 minutes of initial collapse, walls of water would strike the coastal city before most people could understand what was happening. Coastal neighborhoods would be completely inundated, with water surging kilometers inland and overwhelming everything in its path. Buildings would be swept from foundations, infrastructure would collapse, and entire neighborhoods would simply cease to exist. Potential casualties could reach hundreds of thousands. But Catania would only be the beginning. The tsunami would spread outward across the entire Mediterranean, losing some energy but remaining devastatingly powerful. Calabria on Italy's southern mainland would be struck within 15 minutes. The island nation of Malta would be hit within 30 minutes, with waves overwhelming low-lying coastlines. Greek coastal cities would face impact within 1 to 2 hours, and North African shores would receive destructive waves, devastating ports, and tourist centers across hundreds of kilometers. Scientists predict the collapse would unfold in multiple terrifying phases. After upper slopes fail and trigger the initial tsunami, deeper sections near the coastline would follow as structural support disappears. Each successive collapse would intensify the tsunami's power, with secondary waves possibly more destructive than the initial impact. These follow-on collapses could continue for hours, sending wave after wave and preventing any rescue operations. The historical precedent is horrifyingly real. Approximately 8,000 years ago, a massive flank collapse at Mount Etna triggered a Mediterranean tsunami that geological evidence shows reached distant coastlines. That ancient event occurred when population density was minimal. The same process today would impact millions living in densely populated coastal zones. A 5-minute warning is impossible for mass populations to act upon. Emergency services would be overwhelmed. Roads would become instant gridlock. The catastrophe would be over before most people understood it had begun. Given the immense risk facing Sicily and the broader Mediterranean region, Mount Etna has become one of the most intensively studied volcanoes on Earth. The INGV Catania Observatory operates an extensive network of sophisticated instruments measuring every aspect of the volcano's behavior around the clock. High-precision GPS stations track ground movement across the mountain with millimeter-level accuracy, detecting even the slightest shifts that might indicate accelerating collapse. Gas emission sensors continuously monitor volcanic gases escaping from summit craters and flank vents, providing early warning of magma movement beneath the surface. Seismic networks record every tremor and earthquake, from tiny microquakes to larger events that shake buildings across eastern Sicily. European Space Agency satellites equipped with advanced radar systems pass over Mount Etna multiple times per week, using interferometric techniques to detect terrain shifts, measuring just millimeters across vast areas. This satellite data creates detailed deformation maps showing exactly where the mountain is moving, how fast it is sliding, and whether the process is accelerating. Since the 2018 discovery that Etna's flank is sliding beneath the sea as one enormous block, researchers have dramatically expanded monitoring efforts into the underwater realm. Ocean bottom sensors and tilt meters deployed along the Alto Etna fault system record movements, linking surface deformation to deep structural motion occurring kilometers beneath the Mediterranean seafloor. Despite this unprecedented monitoring effort, predicting a gravitational flank collapse remains extraordinarily difficult. Unlike volcanic eruptions, which often provide clear warning signs days or weeks in advance, gravitational collapses can occur with minimal warning or none at all. A collapse could be triggered suddenly by an earthquake or eruption, or occur spontaneously when accumulated stress exceeds the threshold. Fractured rock can withstand. Scientists are exploring early warning thresholds based on rapid acceleration patterns in GPS measurements, sudden increases in seismic activity, changes in tremor patterns, indicating structural failure, and offshore sensors detecting submarine landslide initiation. These warning signs might provide hours of advance notice in the best-case scenario. But the margin for detection is dangerously narrow, and warning time might be only minutes. The response preparedness gap reveals brutal reality. Civil protection authorities have plans for volcanic eruptions, but large-scale collapse and tsunami demand a completely different response system that does not exist. Evacuating hundreds of thousands of people in 5 minutes is logistically impossible. International collaboration has improved tsunami warning capabilities, but all findings point to the same conclusion. When Etna's flank collapses, catastrophe will unfold faster than human systems can respond. Mount Etna has always been in motion, a geological reality that defines the volcano's entire existence and shapes eastern Sicily's landscape. Each eruption reshapes the slopes by adding fresh layers of lava and ash, while simultaneously weakening internal structure. Each earthquake shifts the mountain's foundation, exploiting existing fractures and creating new pathways for gravitational failure. And through it all, gravity pulls the massive southeastern flank steadily toward the Ionian Sea below, a process continuing for thousands of years with no sign of stopping. The movement is slow by human standards, measuring just centimeters each year in most monitoring locations. But the process is completely irreversible once it reaches the advanced stage where Mount Etna now finds itself. Once massive gravitational sliding begins at this scale, once billions of tons of rock start moving as a coherent block under their own weight, nature offers no mechanism to reverse the process or halt inevitable progression toward catastrophic collapse. Scientists warn that a major volcanic eruption could trigger rapid acceleration, transforming current slow drift into sudden failure within hours or days. A large earthquake rupturing the Alto Etna fault system could destabilize the entire flank instantly, sending the mountain crashing into the Mediterranean without warning. The 2025 volcanic unrest strongly suggests Etna's internal magma pressure is building to dangerous levels not witnessed in decades, creating conditions matching patterns observed before historical flank movements and major structural failures. The timeline uncertainty is perhaps the most psychologically difficult aspect of the threat. Catastrophic failure might still be centuries away, occurring so gradually that dozens of generations will witness the slow-motion disaster. The mountain's structure might gradually adjust to stresses, allowing sliding to continue indefinitely without sudden collapse. Or the next major earthquake could trigger instant failure tomorrow, next month, or next year, giving coastal populations absolutely no realistic opportunity to escape. Over 1 million people currently live in Mount Etna's shadow, their entire lives built on land that satellites confirm is sliding toward the sea. Catania continues expanding despite the threat, with new construction proceeding as if monitoring data does not exist. Sicily's economy depends heavily on tourism to volcanic landscapes, with thousands of visitors annually hiking Etna's slopes, completely unaware they are walking on a slow-motion landslide. Development continues in high-risk coastal zones, with valuable beachfront property commanding premium prices, even though it sits directly in projected tsunami inundation zones. The economic reality creates political pressure against sound safety planning. Sicily's fertile volcanic soil supports agricultural operations worth billions annually. Tourism generates massive revenue. Relocating populations would be economically catastrophic. Political leaders face intense pressure to downplay risks, because honest threat assessment would require politically and economically unacceptable actions. The scientific consensus is absolute. Collapse is inevitable. The debate centers on when, not whether. The Mediterranean will face a major tsunami from Etna's flank collapse. The only unanswered question is whether catastrophe happens in our lifetimes or our grandchildren's lifetimes.